Lesson 1-1, functions and continuity. First thing I want to look at today is what is a function. And I like the picture here of a machine because that tells you more about what a function does. So in a function, you're going to have this input. You're going to put something into a machine that you have here. And inside the machine, it's going to do something to the input. So we call that a rule. So it's either going to do some kind of operations on it, and then you get an output. And the output gives you a new product that came from the input. So definition of a function is just a description. It describes a function describes the relationship between the input and the output values. The input is also known as the domain, and that's the set of all x values that you'll be evaluating. And usually for a function, you always get to choose the domain. The range is you're known as the output, and the range is the set of y values, the actual results from the evaluation of a function. If each element of a function's range is paired with exactly one element of the domain, then the function is one-to-one. So if I go back to this picture here, and I look at the domain and range over here, you can see I have one arrow from the domain matching up with exactly one range. So there's only one arrow here, one arrow here, one arrow here, and one arrow there. But if I go the opposite direction, 0 is one-to-one, 1 is only matching up with one number, but 4 you can see is matched up with two different numbers. So this is not one-to-one. So for one-to-one, it has to be exactly one domain with one range and one range with one domain. So let's take a look at an example. We want to identify the domain and range of the function. So the first one here, the one on the left, they're the same, both of them are the same graph. But the one on the left, we're just looking at the domain, which are all x values. And since I can go to the right and I can go to the left, and it will still land on the blue line, if I were to go all the way down here, this one would continue down here, and eventually this, whatever x is, that would be 1, 2, 3, 4, 5, -5. -5 would have a y value way down here. So I can put any of them in there, and that will be all real. It just means I can put any x value in there, and I can find a y value for it. Now the range, there's going to be a limit. You can see the highest points of this parabola is at the origin. So we would say that y is less than or equal to 0. And an easy way to do with the range is just know, how do you know if it's going to be less than or equal to or greater than or equal to? It equals it because it does land on 0, 0, and arrows point below that point. So that's why we would say is less than. It's always looking at the arrowheads, wherever it's pointing, where the graph is going. So moving on to the next one. Consider the graph of f of x shown. Find the domain of the function. So here the domain, again, the domain is always our x values going in both directions. I can put any x value in there and it will land on the blue line. So the answer for this one would be all real numbers. Now moving on to the range. Find the range of the function. I need to find the highest point or the lowest point. So here I'm going to find the highest point, which is here and here. They both are the same. So where on the y-axis is that? That's at 1, 2, 3. We know that it's at 3. And is it going above 3 or below 3? Well, the blue line is going below 3, so we know it cannot be B. We know it's not D. The reason why we know it's not D because this has an X here. That's referring to your X coordinates. So we know it's not there. It can't be C because that means I can put any value of Y. I'll get any value of Y. But here you can see on our graph that it's everything from 3 and below. So our correct answer would be letter A. Y is less than or equal to 3. Next, use the graph to find the domain and range of this function. Here we have a linear function. For linear functions, as long as it's not vertical, linear function is going to have a domain of all real numbers. And then the range, it keeps going up in both directions, or going up and then it goes down. And it keeps going, and this one would keep going up, and this one would keep going down. So this one would also be all real. So most linear functions are going to have a domain and range of all real numbers. Moving on to example 2, identify one-to-one functions from tables. So here it says the table shows the number of medals the United States won at 5 Summer Olympic Games. So you have the years over here, and then you have the number of gold medals, number of silver medals, and the number of bronze medals. So if you were comparing the number of gold medals with the year, you can determine if this is one-to-one. So that means the year matched up with the number of gold medals, and the number of gold medals matched up with the year. So analyzing these functions, we're just going to be looking at gold and silver for this particular problem. We're going to look at the domain and range. So the domain will be the year, and the range would be the number of gold and the number of silver medals. So if we think of gold first, we can just look at these numbers here. Each year is listed once, and it's matched up with a specific number here, with one number. But now if you go the other direction, the number of gold medals to the number of year, you'll see that 46 is mentioned twice. So 46 can't be in 2016 and 2012. And the same thing with 36 can't be matched up with 2004 and 2008. So for gold, this is not one-to-one. What about silver? So if we're looking at these metals, you'll notice that nothing repeats in the number of silver metals. They're all separate numbers, and the years are all separate. So for silver, we would say that this would be one-to-one. And then if we were to do the domain and range, if I did the domain for the gold, the domain would be the year, and the range would be the gold medals. And then for the silver, we would have domain being the year, and the range would be the silver medals. Next, the table shows the 5 largest states by population and the number of U.S. representatives from each state. Consider the function of representatives based on population. So part A, what are the domain and range of the function? And part B, state whether the function is one-to-one. So for here, the population is going to be, or the domain is going to be the population, and the range is going to be the number of representatives. So if I did the domain, I would just list all my domain numbers, which would be 37.25, 25.15, 19.38, 18.80, and 12.83. The range would be the number of representatives, so we would have 53, 36, 27, 20, we only have to list that once, so 27, and we would have 18. Now to determine if this is one-to-one, you'll notice here that 27 representatives is mentioned twice. That means if you go from representatives to the population, 27 would be matched up with two numbers. It would be matched up with 19.38 and with 18.8. So no, this would not be one-to-one. Next, says determine whether each function is one-to-one. So for here, another way to determine if it's one-to-one from a graph, you can use the horizontal line check. The horizontal line check would just be doing, well, first, to make sure that it's a function, you can use the vertical line test. So this passes the vertical line test. What about the horizontal line test? If I cross it over once, does it cross in only one place? And that would be, yes, it would only cross in one place. So yes, this one is one-to-one. Letter B, g of x. If we were to do the same thing, so the vertical line test, yes, it passes. The horizontal line check, it does not pass because it crosses here in two places. So one y value has two different x values. So we would say, no, this is not one-to-one. And letter C, for h of x, do the vertical line test. Yes, it passes. And the horizontal line, yes, that passes. So yes, this would be one-to-one. Next, determine whether these functions are one-to-one. Again, just using the vertical and horizontal line check. Does not pass the horizontal, so no, this would not be one-to-one. The next one for B, horizontal line check and vertical line test, yes, that passes. Next one, vertical, yes, horizontal, yes. Next one, vertical, yes, horizontal, no. Now you should recognize a little bit too that if it's got a parabola shape in the graph, it's more likely not going to be a one-to-one function because it's either going to pass, well, it will pass the vertical line test if it's opening upward or downward, but it will not pass the horizontal line. Next part of our lesson is looking at the continuity part. So here we're going to be looking at discrete and continuous functions. The functions can be discrete, continuous, or neither. So sometimes the type of function that models a real-world situation is determined by a constraint. A constraint is just a condition that a solution must satisfy. Situations where only some numbers are reasonable are often modeled by discrete functions. We're going to look at the different kinds of graphs and how you can determine if it's discrete or continuous. In this picture here, you can see the difference with a discrete, and then over here, those with continuous. For discrete, those are just separate points where they're not attached to any line. They're just separate points with gaps in between. For continuous, it's just one straight line. So think of your pencil and you're just drawing a line and it keeps going. There's no jumps, no gaps. It's just one continuous line. It can change direction. It's just that there's no breaks in the line. Continuous function is a graph with a line or an unbroken curve. So like the example I just drew. A function that is not continuous is a discontinuous function. And an example of a discontinuous function is a discrete function. So here they're just individual points that are not connected. Now there is a function that could have, you could have a line that there's some points that are connected, but then there's some points that are not connected. We would consider that neither discrete nor continuous. So we're going to take a look at some examples here. We're going to look at the graph and then determine whether each function is discrete, continuous, or neither. And then we're going to state the domain or range of the function. So for letter A, we can see that the line is a continuous line because there's no gaps, no jumps. It's just one continuous flow. So we would say this is continuous. And the domain and range, the domain would be all real because it keeps going to the right and to the left, and the range would be all real as well because it goes to positive infinity all the way down to negative infinity. Letter B, you can see that there's a hole in our line here. Because there's a hole in there, there's a jump, but there's still a gap, and the rest is continuous. So this one would be neither. To identify the domain and range for this one, the domain is all real except I can't have 2 x equaling 2 because if x equals 2, it hits this gap, that hole in their line. The range would be all real except, now if I go straight across on the y-axis, that would be y equaling 1. Like y cannot equal 1 for that one. And letter C here, this one just a bunch of random points, so this would be discrete. And then the domain we would just list all the specific x values in here. So I'll just list them from left to right. So we'd have -3, this would be -2, this would be -1, then we would have 1, we would have 3 and 4. That would be our domain, and then our range goes from -3, we have -2, we have 1, 2, 3, and 4. And that would be our specific range, domain range for those points. So if it's discrete, you're going to have specific numbers for the domain and range. Next, examine this function, determine whether the function is discrete, continuous, or neither, and then state the domain and range. You can see this as one continuous flow without any jumps or gaps. So we would say this is continuous. This is a parabola shape, so the domain is all real. And the range has a low point, and the low point is at -3. So it goes y is greater than or equal to -3. Next example. Determine whether the function that follows the cost of coffee beans is discrete, continuous, or neither. And then state the domain and range of the function. Now for this one, if we look at the weights, you can go up to 2 pounds. So from 0 to 2 pounds, you have one cost, which is $8 a pound. After that, then it changes the specific amount. So 2.5 pounds, you pay $20. For 3 pounds, $22, and 5 pounds, $35. And there's nothing in between for that one. So you have a continuous flow up to 2 points, but then you have discrete. So if you have a combination of both discrete and continuous, this would be neither. Now the domain for this one has a couple parts to it. It's going to be 0, it has to be greater than or equal to 0, but less than or equal to 2. Or you could also have x equaling 2.5, 3, and 5. Those are the only possible domain you can have for the weight of the coffee. Now the range would be the price, and the range for this one would be y is going to be greater than or equal to 0. So if you buy 0 pounds, then it's 0 times 8, which would be 0, or less than or equal to 16, because if you buy 2 pounds, that would be 2 times 8, which is 16. Or you could have y equals 20, 22, or 35. Moving on to our next part. Maru offers art and design services. He charges $150 for up to 2 hours of work, $250 for 2 or more hours, but less than 4 hours, and $300 for 4 or more hours, but less than 6 hours. He does not have a set rate for 6 hours or more. Is the function that models Maru's rates discrete, continuous, or neither discrete or continuous? And then what are the domain and range of the function? For this one, you do have some continuous. So for up to 2 hours, you can pay $150. But then there's a jump from 2 or more hours, but less than 4 hours, it's $250. And then you have another jump from $300 for 4 or more hours. So you have discrete and continuous, so this would be neither. What are the domain and range of the function? For here, the domain would be referring to the number of hours. So the domain would be x has to be greater than or equal to 0, or not equal to, just greater than 0. So you have up to 2 hours. If you put it equal to 0, that means 0 hours, you'd be paying $150. And then it says not have a set, so he does not have a set rate for 6 hours or more. So it would have to be less than 6 hours. The range, on the other hand, range would be specific amounts. You only have 150, 250, and $300. Those are the only amounts that you would have to pay. For our lesson, talking about set builder and interval notation. So how are you going to write your domain and range? So sets of numbers like domain and range of a function can be described by using various notations. Set builder notation, interval notation, and algebraic notation are all concise ways of writing a set of values. What I was showing before was algebraic notation. So consider the set of values represented by the graph below. This is showing an open circle at 2, and the arrow is pointing to the left. So this is saying that x, or whatever variable I want to use, I would just say x is less than 2. It can't equal 2, but it has to be less than 2. So how can we write it in each of these different notations? So in algebraic notation, the sets are described using algebraic expressions. So you would just write in x is less than 2. But for set builder notation, that's similar to algebraic notation, but you have braces that indicate the set. And the symbol, this bar line, is just read as such that. So in set builder notation, you would have braces, and you would read that as x such that x is less than 2. So you're just putting what you did in algebraic notation, just put that in braces, put the x such that x would be less than 2. That's set builder notation. And the third way is an interval notation. These are described using endpoints with parentheses or brackets. So you use parentheses here to indicate that the endpoint is not included in the interval. So if it's an open circle, or if it's infinity, you use parentheses. You use brackets if it can equal that. So an example here. We need to write the domain and range of the function in set builder and interval notation. So set builder, first, if I do the domain would be x such that x, I'm going to say it is an element of all real. That is one way to say that. Or you can just say x is all real numbers. The range in set builder notation would be y such that y is greater than or equal to -6. Now in interval notation, we would do the domain as, since it's all real numbers, I'm going to use negative infinity and positive infinity. And with the infinities, you use parentheses. So on the left, the low side is negative infinity. To the high side on the right-hand side is positive infinity. And then the range, this would be on the low end, it is -6. So it can equal -6. So I would have -6 with brackets. On this side, it goes to positive infinity, and I would use parentheses. Next, state the domain and range of each of these functions in set builder and interval notation. So first off, the domain, we'll do the domain in both forms first and then the range. The domain in set builder would be x such that x is an element of real, so all real numbers, or you can put it as negative infinity to positive infinity with parentheses. The range in set builder would be y such that y is less than or equal to, the highest point is 3, so it's less than or equal to 3. In interval notation, we would have, on the low end, it would be negative infinity with parentheses, and on the high end, it would be positive 3 with a bracket. The other one here, this would be domain in set builder notation, x such that x is all real. And then in parentheses or interval notation, negative infinity to positive infinity. And then the range, this would also be y is such that y is all real. And then we would have in parentheses negative infinity to positive infinity. Next, these domains are the domain and range in this one in interval notation. So for the domain, this one would be all real numbers, so negative infinity to positive infinity with parentheses. The range, it does have a high point. So the high point would be, it can equal that, so that would be a bracket. And that is when y is 0. And on the low end, it's to negative infinity with parentheses. Next part, write the domain range of the function in set builder and interval notation. You'll notice that in these examples, you have two different parts. So these are discrete functions or discontinuous functions. There's a gap in them. We're going to write the domain and range for each one of these. So the domain for this one, in set builder notation, we have x is greater than or equal to 0, because if this is 0, it goes to the right. It can equal that, or x would be less than -1. And it's just less than because we have a hole here. There's nothing between 0 and -1. So that would be in set builder notation. In interval notation, we would have to do each one separate. So we would have parentheses from negative infinity up to -1. It cannot equal -1 because of the hole there. And then we would use the union symbol. And then the other one, it can equal 0. But on the high side, that's positive infinity, which would be parentheses. The range in set builder notation, we would have y such that y is, so if we look at the top one, the y is greater than or equal to 2, or on the low end, it would be y is less than -1. And then put that in interval notation. For interval notation, we would have negative infinity to -1, all in parentheses, union, and then we would have brackets 2 because it equals 2, and on the high side that would be positive infinity with a parentheses. Next is the domain range and interval notation. We'll do set builder notation for domain. So for this one, from left to right, so we would have x such that x will be less than -1, or x is greater than or equal to 1. And in interval notation, I would have negative infinity to -1 with parentheses because it can't equal any of those. Actually, not -1 would be +1. And then union. And on the other one, we would have brackets. On the low end, it's -1. High end, it's positive infinity with parentheses. And then the range and set builder notation, the range would be y such that y is less than 1, or y is greater than or equal to -1. Now, if you look at this one very closely, if it's less than, if it can be less than 1 but greater than or equal to -1, it actually includes all the numbers because it includes everything 1 and above. Here includes everything below -1. So the range for this one would actually be y such that y is all real numbers. So instead of writing it this way, which is correct, we would just want to put it in a simplified form, which would be y is all real numbers. Now in interval notation, we would write that one as negative infinity to positive infinity. Next, our last question. Here, the state, the domain, and range of this one is builder in interval notation. So the domain in set builder would have x such that x is less than or equal to 1, -1, or x is greater than or equal to a +1. And in interval notation, this would be on the low end, be negative infinity to -1 with a bracket union. And on the low end, we got 1. And on the high end, positive infinity with parentheses. And then the range in set builder would be y such that y is all real numbers. And in interval notation, we would write this as negative infinity to positive infinity. That is our lesson on functions and continuity.